So in today's first example, we're going to imagine using two different tools, such as a 12-inch ruler and a continuous measuring tape to measure the length of your classroom, or say the width of a basketball court in inches. So the first question, you don't have to answer that with a complete sentence, but should the two measurements be the same? Should they be the same? Yeah, this is not a trick question, guys. Should they be the same? I'd like some participation. Yeah, they should be the same. Now, why might they be different? I'll take volunteers to start, and if I don't get enough, I'll voluntold some people. Yes.
If you're doing the ruler, then you're gonna have to like pick it up and set it back down. You might add a little bit or lose a little bit.
Yes. So when you pick it up and set it back down, you might be off. You might lose a little bit or add a little bit. Either way, yes.
Rulers have like extra amount on either end usually. Like they have an extra amount of plastic.
Oh, it depends on the ruler. Some of the rulers have that extra little bit of plastic on the ends, and so you've got to make sure you're lining up where the marks stop and where they stop. Absolutely. What else might be a problem with a ruler specifically? Yes.
For long distances, you have to like
Okay, that's not a word. I need complete sentences here.
keep moving it down. Like
Well, that's what Emma was saying. You have to keep picking it up and putting it back down over and over again. You have another thought? Yeah.
It might be slightly different, like
The
the width of the things.
width of things.
Of the little notches.
Oh, it shouldn't be.
But
That shouldn't be a problem. We're assuming the instrument is not, screwed up in any way. Well, let me ask you this. Let's say that it wasn't in this room where we have tiles on the ground. Would it be easy to keep it straight as you're going across? No. It's going to be difficult to go straight across with a ruler. So there's all kinds of things that could happen. Thank you for your ideas. So which tool do you think would give you a more precise measurement?
The measuring tape.
Probably the measuring tape. And again, for all the reasons we just have talked about, all the places where we said things could go wrong were with the ruler, not with the measuring tape. Okay, now, for the rest of this, you're going to work with your shoulder partner or your shoulder partner plus in one case. Below is the data provided by 22 different groups of students measuring the length of a gym in feet. And I've been really nice to you, and I put them in order so you don't have to do that yourself. So let's take a look here. So do the data appear to have any outliers? Or maybe a better question would be, what's a potential outlier at least? The first one, yeah, the very first, the ruler, suddenly that's a 5, and these are in feet, right? That's a 5-foot difference. That's kind of a big difference, isn't it? And then here it's 4 feet. That's kind of big. So these might be outliers. How about at the top? Do these appear to be outliers? The 346 and the 341?
No.
No, they're relatively close to the other data. So possibly, and at this point, we haven't talked about how to determine whether or not they are outliers for certain. Possibly the 312 for the ruler and the 330 for the tape. All right. And again, this tells you that there are 22 different groups, so that should be helpful to you. find the first quartile, the third quartile, the median, and the IQR for both sets of data and check it with your shoulder partner or your shoulder partner plus. Go. All right, anyone need more time to do part B? Some of you started working on time C. Okay. Okay, anybody need more time on part B? Okay. Make sure that your shoulder partner is not wrong. If I call on your shoulder partner and they're wrong, I'm coming after you.
He said that it's in the middle. That he used these.
Oh, medium for tapes could be
Yes,
good.
you do. I know what I'm doing.
Yeah, oh, no, tape is 3/7.
This is the one
My
thing
bad.
I'm actually okay.
Ruler is 3/4, right?
Yeah.
For the ruler?
Is it just a normal box plot?
I'm sorry?
Is it just like a normal box
We all
plot?
messed up.
All
We
is
had
a
to
lot of
use,
Is it
we had to
normal
use
box
these
plot, just a
variables
normal
because those
box
are the
what?
all is a lot of people. I don't miss it.
Yeah, except you're gonna do two.
Look,
You're gonna do one for the ruler and one for the tape
You wanna
measure.
do one right above?
Yeah, so they're on the same set of scale. All right, so let's find out what we know at this point. Let's see. Mr. Johnson, what's the median for the first one?
For ruler, that
Yes.
would be 334.
That's what I got. And then, let's see, desk 8. Barrett, what'd you get for quartile 1?
322.5.
I disagree with you on that. Tell me how you found it.
Because I know what because I didn't count the ones in the median. Or not the.
So you didn't count the 334?
I did what Ben and Sammy did.
Okay, but I don't know what they did. So
What
Mike,
we did
all right, wait, whoa. I'm asking him. So,
I don't know how to explain what I did.
so did you, when you're finding quartile 1, did you not include the 334?
No.
Okay, so we are going to include the 334 because on this, to find the median, we were actually averaging these. Right? So we still keep these numbers in the data set. It's a little different. We don't throw those out. Do you see what I'm saying? So we keep this 334 as part of the lower half of the data and this 334 as part of the upper half of the data. Do you understand what I'm saying?
Yeah.
Okay. Bless you. And then let's see. Nobody's sitting in that desk. So, Cooper, what did you get for quartile 3?
340 for the world.
I'm sorry?
For the ruler, 340.
340? Yep. And then the interquartile range will just be the difference between these two will be 6. And then for the tape measure, let's,
16.
I'm sorry? Oh, 16, not 6. Thank you.
It's 324 for the quartile one.
Yeah, 323.
Oh, did I write 334? Thank you. I wish I could say I was, doing that to see if you were paying attention, but I wasn't paying attention. All right, Sammy, what's the median for the tape measure?
337.
Yep, it's 337. And then Christian, what's quartile 1?
336.
Yep, it's 336. And quartile 3, who's in desk 9? Sophia. Yep, 339. And the interquartile range here is only 3. Okay, any questions about how we find those? Yeah.
For box, question for box plots. For box plots, do we always have to start with 0?
No, we do not. Fact is, I would suggest strongly that you don't start with 0 on this. Yes?
I'm confused on what parallel box plots mean.
All right, well, so we're getting there. Just hang on. So for parallel box plots, we're just going to draw 2 box plots, one over the other that will be parallel to one another.
The same some numbers.
So on this, we need to start at 310 and go to 350. Is there enough room for us to go by 5s then? Like 310, 315, 320, 325, 330, 335, 340, 345, 350. We could have we could have made our width between them be less. Don't do it by tens. It's going to be so small that it's going to be hard to make any comparison. You'd like to use as much of this as you can. We probably could have gone by threes and done just as well. Let's see, our minimum is 312 for the first one. Since that's not at one of these lines, we must label it. And then quartile 1 is 324. And the median was 334. And quartile 3 was 340. And the maximum was 346. So it looks something like this. And that is for the ruler. You should label what you're doing, not just do it. And then for the tape measure, we start at 330 is the minimum. And then 336 is quartile 1. The median is 337. Quartile 3 was 339. And the maximum was 341. So if you look at the box plot, it's easier to answer the second part of B. Which set seems more variable? Which set seems more variable? The ruler or the tape?
The ruler.
The ruler is way more variable. Partly you can tell that from the interquartile range. A bigger interquartile range means there's more variability. But then when you look at the box plot, it's really obvious. Okay? We got much more consistent results with the tape measure than we did with the ruler, which is what we expected. All right, let's go on to page 2. This is where having a partner is going to be helpful to you. I want you to make a stem and leaf plot for each of the data sets. So help each other out.
2 is
But what is that?
0, 1, 4,
It says
8, 8, 9. Yeah. 43, 0, 0. Awesome. Good luck. Good reading. Thanks so much.
So it doesn't fit.
Just make a histogram.
It's like a histogram. One.
We're doing so much for this
What
thing.
is the range?
All right. Let's see. Bella, could you read to me the numbers you have for the ruler after the 31?
2, 7,
Oh, you got to read it slow enough to where I can write them all. 2, 7,
and then 9.
and then 9. Thank you very much. After the 3, 2, Mr. Bryant.
0, 1, 4, 8, and 9.
And I'm going to point out to you something. There are a couple of you who aren't particularly neat by nature, where you just have this list of numbers after them. These must be directly over one another, or you will lose points on that. I suggest that when you do them on homework and stuff, Johnny and I were talking about this. If you'll use graph paper and just put one number in each square, that automatically aligns them. Okay, Sammy, what'd you have after the 3, 3?
0, 0, 4, 4, 4.
Whoa, 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 whoa! Remember, I gotta be able to write this. You said 4, 4, 4. So 2 zeros and 3 4s.
No.
3 zeros, 2 4s.
Wait.
2 0.
You're killing me, Smalls.
Yeah, 2 zeros, 2 4s.
All right, shh.
2 zeros, 3 4s.
2 zeros, 3 4s. That's what I asked.
Then 5, 7, 8.
And then 5, 7, 8.
Yes, sir.
Thank you. Emma, tell me about 34.
0, 1, 1, 3, 5, 6.
That's it? Okay. All right. And then the tape measure. This gets ugly, doesn't it? Because one of these is really long. Which one is it? Is it the 3 3s or the 3 4s that's really long?
3, 3.
The 3 3s?
4, 5, 5, 6, 6, 6.
All right, stop. No, shh. So, one of the things that you'll sometimes see done with this is they'll split it. So, Cooper, could you read me just slowly? Start reading me the numbers.
0, 4, 4, 5, 5, 6.
All right. And then what I'm going to do is I'm going to do the next ones down here. Go ahead.
6, 6, 6. There's 5 sixes.
There's 5 6s. Yoinks. Okay, go ahead. Thank you.
7, 7,
Thank you, sir. So you'll see this on stem and leaf plots sometimes. If you have one that's exceptionally long in the leaf, you can divide it in half. Okay? Christian, how about the 34?
0, 0, 0.
Two ones, Christian. 2 ones.
I can't read.
Okay, Paul, help him out.
1, 1. That's all.
And that's it?
Yeah, that's all.
Okay.
Will that be all?
All right. So what range had the greatest frequency in both? Well, from 330 to 349 or 339. Right? And these two put together. So the majority of the measurements were between 330 and 339, or I shouldn't say the majority. There were more of those than any other type. All right, so now let's make a histogram with bin widths of 5. We're going to use the same scale on each horizontal axis. So we'll start with 310 on both of them. So again, what you would do is you draw that little heartbeat thing, which says I'm not starting at 0. And we want bin widths of 5, so that's 310. Because this is so small, I'm going to not write in for every one of them. And this will be for the ruler. And these would be the counts. So from 310 to 315, we've only got 1. And then from there to 32, we've only got 1. And 320, we've got 3 in the next one and 2 in the one after that. And then we've got 1, 2, 3, 4, 5, 6 in the next one. Oh, does the 5 go in the next one, or does it go in the one after that? The one after. So 1, 2, 3, 4, 5. And then 1, 2, 3. And then where are we? We're in the 340s now. 1, 2, 3, 4, and 2. So it may be that one or both of these down here are outliers, but there's not a lot of great agreement on that one. There's a fair bit of variation. And we're going to use the same scales here. So we don't even start until the 3 3s, and there's only 3 of those to start with. And then there's a whole bunch. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yikes. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's a lot. And then 4 in the last one.
And like that one extremely high.
Yeah. So notice, just like we saw in the other ones, way less variability in the tape measure. Okay, now, one of the things you'll be asked to do sometimes is to describe the overall shape of a data distribution. So this is an example of symmetric. It's symmetric because the right side and the left side both look alike. Symmetric could also look like, this. Now, when we say symmetric, we're not saying it's perfectly symmetric, where the left side and the right side are exactly the same, but we are saying that they're similar.
Wouldn't double peaked be symmetric too?
Double peaked can be symmetric, yes. Here we've got a skewed distribution where it's high on one side and low on the other. This is single peaked, so is this. Right? This is also a single peak. This is double peaked, sometimes called bimodal. And this is uniform. Uniform means everything is the same. They're all about the same height. Again, not perfectly uniform, but they're about. So, how would you describe our two data sets? So, let's look at this one. Is it symmetric?
Single peaked.
Yeah, it's kind of got a single peak. It's kind of a mess. It's close to being symmetric. Right? The right side and the left side kind of look alike. What about this one? Yeah, very much single peaked.
Nah, just a bit. Just a bit.
What about symmetric? It's pretty symmetric. I mean, yes, this one's 4 and this one's 3, but it doesn't have to be perfect. Okay? Statisticians are a little different than most mathematicians in that they're like, yeah, we don't expect things to be perfect. Mathematicians are like, things need to be perfect.
My dad says math is the only perfect thing in the world, and I said, I thought you said I was perfect, and he's like,
Uh-oh.